Hi, let's discuss some example of machine instruction. In previous lecture, I already discussed what operation we can do on machine instruction and what are addressing mode. Now I will use operations of machine instruction and addressing mode for writing machine instruction. So before starting this lecture, first go through previous lecture, then come to this lecture that you can understand. First example, x equal to y plus z. I will write machine instruction for this. First, I need to load y into register LD R0Y. LD stands for load. So this means y will be assigned to R0. Next, I can load Z into register or I can do the direct addition. We can do addition from two locations, one from register and another from memory. Let me do direct addition. So add R0, R0, Z. Whatever the content of R0, that will be add with Z and result will be stored in R0. So R0 equal to R0 plus Z. Now R0 contain Y plus Z. Again we need to store R0 content into X. So next statement will be STX R0. It means X equal to R0. Let's see another example. Example 2. X equal to Y minus Z. Let's see another example. X equal to Y minus Z. First I will load Y into one register. Let load R1Y. Now R1 contain Y. Next, I can load Z into register or I can direct subtract. Let me load Z into register. So load R2 Z means Z value will assign to register 2. Next, I will do the subtraction. So sub R1 R2 and that result will be stored in R1. So sub R1 R1 R2. It means R1 equal to R1 minus R2. Now subtraction is done. Now R1 contain result of Y minus Z. Next I need to store into X. So store X R1 means whatever the content of R1 that will be stored in X. At starting we'll always load and at the end we'll store the result. Now what is the difference between these two? Here there are 3 instructions, here there are 4 instructions. But which one is faster? Here we are using a memory location. So Z is a memory location. For doing addition, one operand is in register, another operand is in memory location. So to access from memory location, it will take more time. Here both operand are in register. So it can do faster subtraction than this addition because here we are accessing from the memory. So you can say here there are 4 instructions but still it will be faster as all the operand are in register. Here one operand is in register while another operand is in memory. I already discussed in previous lecture in code generation that we are writing code for two type of machine. One is RISC, another is CISC. RISC uses 3 address instruction while CISC uses 2 address instruction. All the code I am writing is for RISC. All are 3 address instruction. Let's see another example. A equal to B plus C and another statement D equal to A plus E. Now first we will write for this A equal to B plus C. First thing we need to load the operand into register. So load R0B means B content will be loaded to register R0. Then I can do direct addition or I will load C into register. Let me do direct addition. So add R0 R0C means R0 content will add with C content and that will be stored in R0. Now R0 contain B plus C. Next I need to store. So STA R0, whatever the R0 content that will be stored in A. Next statement D equal to A plus E. There is a operand A. For that we need to load again A into some register. So load R0 A means we load A content into register R0. Then we can do direct addition or load A into register. Let me do direct addition. So add R0 R0 E. Now R0 content A plus E. Next we will do the store. STD R0. It will store R0 content into D. You can mark there is a redundant code. Here we are loading the value that is immediately stored. A value was immediately stored. Now again we are loading. So if one variable is live, like A is live here, A have some next use, then we should keep it at register that we can further use it. So the for statement is a redundant since it load a value that has just been stored. It load a that has just been stored. We can remove this, and we can remove this. If we'll remove this, now this R0 contain A, and next we can use the R0. So we can reduce this code by just removing the store and load. The quality of the code is determined by its speed and size. There should be less number of machine instructions and it should be faster. In example 1, there are 3 machine instructions. In example 2, there are 4 machine instructions. But example 2 machine instruction is faster than example 1. So if the target machine has an increment instruction INC, then 3 array statement A equal to A plus 1 can be implemented by just single instruction INCA. INCA means whatever the A content, that will be increment by 1. If the target machine don't support increment operator, then we need to write machine instruction for this. First we need to load A into register, so load R0A. Then we can do the addition, add R0 has 1. For number we used hash symbol. Now R0 contain the addition. Next we need to store. So store A R0. We are writing 3 machine instruction for this single instruction. So if your machine support increment, use this operator rather than this 3 statement. Next, I will write some machine instruction for array. Suppose A is a array whose element are 8-byte value. Let it be real number, and also assume that index starting at 0. First example, B equal to A of I. So this is a array. So what we will do? So first we will load I into register. Let LD R1I. We load this I into register R1. Then I need to multiply I with 8. So multiplication R1 8. Next I will write for this array, load R2 A, then bracket R1. So what is the meaning of this? Meaning of this is whatever the content of R1 plus A, then that content. So content of R1 contains some location. That location will add with A, will get some another location, and that content will be loaded in R2. Now for array is done, next we will store. So store B R2. Whatever the content of R2, that will be stored in B. This is a index address. I already discussed in operator for machine instruction that we can write for array and also we can write for pointer. Index address used for array while integer index is used for pointer. Let's see another example, A of j equal to C. So let me load C into R1. So R1 contains C. Next I will load J into another register. Let R2 load R2J. Next I need to multiply J value with 8 as I am considering size of each data is 8. So multiplication R2 8. R2 equal to R2 multiplication 8. Next I will do this operation. Store A of R2 R1. Whatever the R1 contains C, that will be stored in A of R2. What is A of R2? Content of R2 plus A content. Why we are multiplying with 8? As I know, one dimensional array location formula is L0 plus I multiplication C. L0 is the base address, I multiplication C, C is the count or size. Here size is 8 byte, that's why we are multiplying with 8. You can also write for 2-dimensional array and for 3-dimensional array. You just need to know what is the location formula for that. How we are storing 2-dimensional array in memory as 1-dimensional array, and how we are storing 3-dimensional array in memory as a 1-dimensional array. If you know that location formula, you can write machine instruction for that. I already discussed how to write 3 address intermediate code for 2-dimensional array and for 3-dimensional array. Just ref for that, you can easily write machine instruction. Let me do for pointer. X equal to pointer p. To represent pointer, we'll use a integer index. So first we'll load p into register, load r1 p. Now r1 contain p. Next load r2 0 of r1. What is meaning of this? Whatever the content of R1 that will be add with 0, then that content that was held by R2. Next, store x of R2. So now this pointer p that is in R2 will be stored in x. This is the integer index address that we are using to represent pointer. I already discussed what is integer indexed address. Just go through that, you can understand. Next, example 8, pointer p equal to y. First I need to load p into a register R1. Then I need to load y into a register R2. Next I will store y content into pointer p. So y content is in R2, and this thing we can write in pointer representation that store 0 of R1 R2. R2 contain y and 0 of R1 that is content of R1 plus 0, then that content. So whatever the R2 content that will be stored in this pointer. Let's see one conditional statement. If x less than y, go to L. So first we need to load x and y. Let load R1x. Now R1 register contain x. Then load R2y. R2 register contain y. Next we need to do x less than y, but there is no operator for less than. So what we will do, we'll subtract. Sub R1, R1, R2 means R1 will contain R1 minus R2. Let x equal to 3, y equal to 5. Then 3 minus 5, it will be minus 2. Next we will do branching according to this value. BLTZ means branch less than 0, R1, then go to level L. So if this R1 means if this subtraction result is less than 0, yes, this is less than 0, then go to level L. Suppose x value will be 6 and y value will be 5, then 6 minus 5 will be 1 and 1 value will be greater than 0. In that case, this condition will be fail. So if R1 value is less than 0, then branch to L, means jump to level L. I discussed 9 examples of machine instruction that is enough for compiler. You will see more detail in computer organization. If this lecture is helpful for you, please like and subscribe. Thank you.